Log on, tune in, find out. Another good idea from Cambridge.
Our main job for the day was to construct, actually it's a family of families of Green's functions for the Laplacian with a specific behavior on the boundary, namely they vanish on certain pieces of the boundary. So if this is C, this is B omega minus, this is B omega plus. And as I mentioned, similar construction works in that situation. This is crucial for the partial data result, and it's where most of the work goes in. And this is just a bound. And so far, we've basically achieved 1, 2, and 4. In lemma 1, where we've constructed an operator. For every f there is a u. U solves the PDE. Its trace is 0 where it's supposed to be. Sorry. And there's this extra property that pi tau hf is 0, where pi tau, do we still have a pi tau around? Yes, pi tau is the orthogonal projection on the null space for this problem. So h tau, if you wish, is perpendicular to this null space. Now we want to give up on that property and instead obtain property 3. And the claim is that this is what works. So this is now the sketch of proof of the theorem. So property 1, what is L tau G tau F? So it's L tau H tau F plus L tau pi tau times H minus tau F. L tau of H tau F is F, since H tau is a Green's function or a Green's operator. And anything in the range of pi tau is essentially harmonic. So L tau of pi tau of anything is 0. So 1 is okay. 2 is also okay because the trace of H tau F is supported in d omega signum tau, and anything in the range of pi tau of anything is also supported there. So 2 is checked. 4 follows from corresponding estimate. So h tau has a 1 over tau bound. You saw that also in Gunther's lecture. This is crucial, that the remainder is small for large tau, bound for h tau. And also, this one has a 1 over tau bound. And the boundedness. A projection is a bounded operator with norm 1. And so that's also easy. So the main tricky business is property 3. So I don't know how much of that I should show, but since I've been saying it's crucial, let me show you roughly how it goes. So we want to show that G tau star is the same as G minus tau. Okay, here's the definition of G. What is its conjugate? It's h tau star plus h minus tau. Orthogonal projection is self-adjoint. So the question is this equal to h minus tau plus pi minus tau h tau star? So we're just going to chop at this one piece at a time. The first piece is we're going to multiply on the left by pi tau. So if you wish, think of that as made up of two parts. Let's call it A and B. So 1 minus pi tau. Right, so I've split my Hilbert space into the pi tau piece and the complementary piece, and I checked the identity on each piece. So let's try it on the first one, A. What do we know? We know that pi tau h is 0. So if we take adjoints, this means h tau star pi tau is 0. So h tau star pi tau is 0. h minus tau, pi tau squared is pi tau, since this is a projection. Question, is this the same as h minus tau pi tau plus, and here again h tau star pi tau is 0, so this should be 0. And so the answer is yes. So it remains to check B. Let's go over here and try to look at B. Now, now we're going to multiply by pi tau on the left. So B will have a BA piece, which is, I better write down B before I, so what is B? Oh goodness. Maybe I should just do it on a nearby blackboard. So this we're done with. So what do I need? I need h tau star plus h minus tau pi tau 1 minus pi tau. Is that equal to h minus tau plus pi minus tau h tau star 1 minus pi tau? So this is my B. So B has a part A and a part B. Part A is when you multiply by pi tau. Is that equal to pi tau h minus tau plus pi minus tau h tau 1 minus pi tau? No, not pi tau, pi minus tau in front, sorry. Okay, so pi minus tau h tau star I don't know, but I do not know that pi minus tau h minus tau, according to the construction for h, is 0. So is this equal to pi minus tau? This times that is 0. Pi minus tau squared is pi minus tau. Oops. And the answer is yes, it is. And so what's left to do is 1 minus pi minus tau times that. Is that equal to 1 minus pi minus tau h minus tau plus pi minus tau h tau star 1 minus pi tau? Okay, so summary so far. We want to prove this symmetry property. If you write out the formula I propose for G, that's what that amounts to. And we've reduced it to proving this. So where this is pre-multiplied on one side by 1 minus pi tau, and on the other side by 1 minus pi minus tau. Okay. Well, so how do you prove something like this? Well, you apply this to an f. It's two elements of L2, and so they're equal if they're inner product with some other element. Is the same. H minus tau pi tau, 1 minus pi tau f. Is that equal to H minus tau plus pi minus tau H tau star 1 minus pi tau f. And so we can flip some of that on the w. So we have 1 minus pi minus tau w. Let me see how much of it I want to flip. Yes?
There are no vanishing terms in that formula that you want to prove.
Vanishing terms where?
When pi tau, in the left hand side, when pi tau is again 1 minus pi tau.
And on the right the same page.
Oh, you're saying this part?
This,
This part
that's
cancels
where
this?
vani-
This part cancels this part?
No. That part is actually vanishing. I mean, because you have the projection and the orthogonal. Again.
Pi tau multiplied by 1 minus pi tau.
Oh, here you mean?
Yes. Not that.
Same right.
Pi tau times this. So maybe, yeah, maybe.
And also in the
Right. So okay, so this is where I was. So the point is that pi tau times this should be 0. Maybe I shouldn't torture you with all the details on this. So here, 1 minus, is that? Right? Is that what you're saying? Very good. Okay. So 1 minus pi tau of f, according to lemma 2, 1 minus pi tau is something of the form, or at least a limit of something of the form L minus tau of a v here. So it suffices to show where V is in, let's be careful, V is in d signum tau. If you throw in the 1 minus pi minus tau on the W, this is a pi minus tau, so this will be an L tau, let's call it V tilde, where V tilde is in d minus signum tau. And I can put the H tau on this side as well. So the question is this equal to L tau V tilde H minus tau, and this is L minus tau V. So we've brought it down to this, where V tilde is in d minus signum tau and V is in d signum tau. And then it just amounts to the integration by parts which I had on this board before in the first lecture and got erased. So L tau u V is u L minus tau minus u dv d nu if v on the boundary is 0. So, well, since I'm that close, maybe I should finish it. At least I can say I proved something.
I think you might have missed the V on the
Pardon me?
formula.
What's the question?
You missed the V?
You mean here?
Yeah.
Yes. All right, so where are we? Here's an L minus tau V. So IP means integration by parts, not inverse problem. So use IP with U equals H tau L tau V tilde. Okay, so what do we have? On the left side here, I can write this as, I can put the L tau. You see, the issue is the following. H, the Green's operator, is a right inverse for L. Not a left inverse. Okay? So I have to be careful. I cannot cheat and just say this is V tilde. However, I'm in the right spaces so that in fact it will work out. Okay. So, but what I can do is I put this L minus tau up on here by integration by parts. And now I'm hitting H tau from the correct side. So it's equal to this and V. Now, V, dv d nu, is 0. Let's say tau is positive before we go crazy. Then V is in D plus, if v is in D plus, dv d nu on omega plus is 0. On the other hand, right? So I'm looking at this boundary term. dv d nu is 0 on omega plus, so this is just on omega minus. However, u is h tau of something, and the trace of h tau of something is supported in omega plus. And u h tau of something equals 0 on d omega plus. Sorry, is supported. It's supported where this thing is 0. So this is to say that there is no boundary term when I flip L minus tau on that side. Is this equal question mark to just as I just did, similar integration by parts, again the boundary terms disappear to v tilde L minus tau h minus tau L minus tau v. Okay, what is L tau h tau? Ladies and gentlemen, boys and girls, L tau of h tau. Identity. So this is just L tau v tilde inner product v. Is that equal to v tilde L minus tau of h minus tau is also the identity. Tau can be positive or negative. So this is L minus tau v. So the question is, can I flip the L tau from this into that? And the answer is yes, integrate by parts again. And again, v tilde is in D minus, v is in D plus, and so the boundary terms vanish. Okay, so I essentially gave you a full proof of the theorem. With this, the new Green's function. All right, so what do we do with this Green's function? Well, we do two things. We have a forward problem. Where we're going to construct, to use Gunther's nomenclature, new CGOs. And as I mentioned before, this will be a solution of a harmonic function supported in the back. This is identical to the ones in, let's say, Koenig-Sjöstrand-Ullmann. But out of this, I construct a solution of the Schrödinger problem via this integral equation. And I don't know if this is new or not, but it's based on the Green's function which we discovered. So it may be new. I haven't looked into whether it is or isn't. And again, the main point is that for large tau, this is small, and so you can solve this problem. You have these solutions. And the inverse problem, remember we had the very basic identity which is how we tease out all the information that we could get for the problem from the Dirichlet to Neumann map. So if we use G for V naught, with X first outside as indicated before, so X not in omega and then converge to the boundary, we get Green's function lambda q minus lambda naught u equals Green's function qu, and Green's function qu is u minus u naught. And so this is happening on the boundary. This is the inverse equation on the boundary. Why do I call it an inverse equation? Well, here you have to know Q to produce the solution. Here, you don't need to know Q. You only need to know the boundary data, Dirichlet to Neumann map, to produce the trace of U on the boundary. And as explained, because G is 0 where you don't know that, partial data is sufficient. And so the main problem becomes the solvability of the boundary integral equation. And I don't think I'll have time in 10 minutes to do that. But in particular, would like to remember G, we don't have a function G of x, y. We only have an operator with those properties. So this is what's called a single layer operator. The terminology comes from a very classical potential theory, where you have a Green's function which has to do with the potential corresponding to a point charge. And so this is the potential if you spread these point charges f of y on the boundary. So analytically, the question is, how do we define this? How do we prove it's a reasonable operator when all we know about our Green's function is this? Now, classically, proving boundedness of single-layer operators is work. And if the boundary is not smooth, it's actually non-trivial harmonic analysis. And so it may amuse you to hear how we dealt with this. So maybe this is what I will finish with. Here's our definition of S star. So we'll define S tau as follows. It's equal to, take the trace operator, compose it with our G tau, take the adjoint, take the trace of that, and another adjoint. I will explain why this is a reasonable thing to do, and why we get boundedness of this operator with no new estimates, just using the old Karleman estimate that we use throughout, plus the trace form, the trace property. So let's just talk informally. So you have G tau. G tau is an operator from L2 into L2, but in fact H delta. And so the trace makes sense so what am I trying to prove here? So the theorem is S is a bounded operator from H star into H. So in standard layer potential theory, we know it goes, S is smoothing of order 1. Its symbol as a pseudo-differential operator, it's like integrating once, 1 over derivative. And so it goes from H minus a half to H plus a half. And when you use the standard Green's functions, which are better behaved than these, you can prove with the same proof I'm about to show you, well, proof, I'm about to just sketch it. You can show that in fact it goes from H minus a half to H plus a half. So we know the trace goes from L2 to H. Now what is the trace? Now, informally here, you start from something, an f of y dy. So y is inside, and x is inside. And what's my problem? My problem is that I would like both x to be on the boundary and y to be on the boundary. So I have an operator that takes inside thingies to inside thingies, and I somehow want to turn it into an operator that takes boundary thingies to boundary thingies. Okay, so when I take the trace on the boundary, that's easy. I've achieved that for x. If I take the adjoint of the trace, that's an operator from H star into L2. with kernel g of yx bar, where now x is inside and y is on the boundary. If I take the trace of that, y will be on the boundary, and now x will be on the boundary as well. But to be able to take the trace of it, you need to prove something. You need to prove that as a function of x, this is harmonic. So it turns out that Laplace trace g star h is 0 for any h in h star. Again, the Laplacian hits this x, which is inside. So that's maybe believable, at least at this point in the lectures. So the Laplacian is 0. That means this is not just L2. It's better than L2. So trace takes h star to h delta. And so if I can take its trace again, the trace of trace g tau star will go from h star into h. Okay? And has kernel basically g, y, x, with y on the boundary and x on the boundary. But I want g of xy, so I take another star of that. So this has kernel gxy, where x is on the boundary and y is on the boundary. So I've managed to put both of my x and y's on the boundary. And as an operator, it goes from the dual of this to the dual of that. Trace of trace composed g tau star star goes from the dual of h into the dual of h star, which is h. And so this is the single layer. And that's a sketch of how you prove that it takes the dual of our space H to H. And it's lunchtime.